Okay, hi everyone. So today we're here for a Wolfram Physics Project working session. A little bit of a different setup from previous times. I have been working on a little bit of a project. Mostly I've been doing it on my own. And I thought I would kind of share the process with you this afternoon. We do have a couple of other people here who may help. I'm hoping that folks on a live stream will also help. But usually the things I will be doing are mostly things I will be just quietly doing by myself. Now, for people who are really curious, I've been doing video work logs, where even when I'm just doing stuff on my own, I record the screen, no sound, not audio isn't turned on, there's no sound of me whistling to myself, which sometimes happens, I think, but I don't really know it. But it's just the process of building things up. Okay, so the thing I'm working on right now is kind of a version of Multiway Systems. I'll talk about more details in a minute. Kind of the goal is to produce another one of these Wolfram Physics Project bulletins. This is our kind of approach to kind of what journal publishing was back in the 1600s and what I think it might be again. It's kind of a slightly more informal approach than people have typically had. And these are really bulletins about progress we're making. I mean, I think that's what, and we will be uploading them to places like Archive, but primarily they will live on our site, and we will have a section about Wolfram Physics Project bulletins. So I just put one up today that is here. It's called Exploring Rullial Space, the Case of Turing Machines. And, you know, it was one of these things where it was supposed to be just 2 or 3 pages long. Turns out, in actuality, it's 70 pages long. This, I think, came out pretty interesting. I mean, it's the beginning of exploring this very abstract idea of Rullial space. In this case, in the context of Turing machines, a bunch of interesting things came up. Kind of the group structure of Turing machines, a bunch of things about the group structure. I don't know, I've been struggling getting this group theory right, and I'm not sure it's all completely correct yet. That's another feature of these bulletins, is they are subject to updating. Let's see, coming on down here, some fun stuff. I think I mentioned it in the update on Thursday about being able to actually estimate the value of the maximum speed in Rullial space, those kinds of things. Anyway, this just went up. So given that this bulletin is done, I am on to the next bulletin. And the next bulletin is going to be about multi-way systems based on numbers. So let me switch now more to, let me go ahead and just switch this to just, let me see, how do I do this here? Okay, let me just concentrate on the screen here. And I will show you what I've been working on. And our job for this afternoon is to make more progress on this. I have to say, multi-way systems based on numbers are really kind of cool, and I'm sort of upset that I didn't investigate them years ago. I have one note in NKS about them. Okay, let me show you what I got so far here. Hold on one second. Here we go. Okay, this is my draft bulletin so far. Let me just make this a bit bigger. And everything here is subject to change. And the words, you know, I'm one of these people who, if I'm going to write something, I have to write the introduction first, but then I write the thing, and then I write the introduction again last. But I have to write the introduction first just to give me a sort of sense of where I'm going. And that's what I've done here. Okay, so we'll be talking about where I've gotten to so far and what the current issues are. Okay, let me set the stage here. What are we talking about? So this is a simple version of a multi-way system. It's basically saying, take a state X and iteratively map it to F1 of X and F2 of X. And so if we do that with symbolic F1 and F2, we get a tree that looks like this, okay? So now the question is, what happens if you do that in practice in the wild. So let's take a look at that. Let me show you an example just to get started. This is actually the example from NKS. This is the example of, here, let me open this up. Well, all right, let me do this. Hold on 1 second here. Let me start this off here, make this bigger. Okay, so this is going to be the multi-way system that says n goes to 2n. That thing is our nice little infix form for the function, function. I recommend it. But that just means a function n 2n, n plus 1. Actually, as I was using this in doing this work, I really like this way of representing our, normally that would be, in Wolfram language, it would just function of n, and then the 2n, n plus 1, but I really like this notation here. Okay, let's take a look at what this did. Okay, so, and I'm hoping, let's see, we have Ed here, right? Do we have Ed here?
Yes.
Okay, I'm just making sure Ed is fully on board with what's going on, because I'm gonna need to ask you a bunch of questions soon. Okay, so what we're doing here is we're saying n goes to 2n or n plus 1. So in this case, we go from 0, that maps back to 0 with 2n, and it maps to 1 with n plus 1. Both 1 maps to 2 with both 2n and n plus 1. Here it branches, and so on. Now, what's interesting here is we also get these kinds of mergings, right? Okay, that is our setting. Let me show you what I figured out so far, and then we'll get into research, so to speak. So if I continue this a while longer, so this is, remember, this is just n goes to 2n, n plus 1. If I continue it for like 11 steps, let's say, it'll render it so that the beginning is at the middle there. So first question for this, so I think what I figured out is that the, let's see, this function m sub t, which is the number of nodes that you get to going a distance t from the center, is Fibonacci function of t minus 1. Okay, so what we're going to do, what I'm trying to understand is, okay, question, is this part of a symmetry group? Well, that's an interesting question, isn't it? That's going to come up some more. Let's think about that for a second. Can we think about these as generators of a group? Well, it isn't a group right now because it doesn't have, the inverses are not there. So actually, I'm really curious now that you've mentioned that. Let me try that. Let's try putting in the inverses. So the inverses would be n over 2, I think, and n minus 1. But now that's going to mess things up immediately, right? Because n over 2, as soon as that's, okay, so let's look at this going just for 3 steps. Let me just label my thing here. Let's see, physics, working material, 2020. Where is it? I have to keep this organized. And these things, by the way, people probably might have noticed, these are getting uploaded every day, whatever I've been doing. So this is Multiway Numerical 03. Oops, Multiway dash numerical 03. Okay, so actually, I don't even understand why this worked. Why did we not start getting n over 2s? Oh, I bet we do. I bet some of those things are rational numbers. Yes, they are. So this is going to be very interesting. We'll look at this. Good idea. Thank you for that suggestion. One question would be, can we make something which has inverses, right? In general. So for example, in this case, if we just had, let's try this. Let's say n plus 1, n minus 1. Let's just do that one to begin with. Okay, we get that. Okay, so that is a group case. Let's say we also have n plus 2 and n minus 2 here. That's a big mess. let's try taking, let's say, n plus 5, n minus 5, see whether that generates something different. Ooh, that's generating a grid. Okay, so let's take a look at this guy. So let's look at that guy running a bit longer. Instead of 3 steps, let's try 6 steps here, and let's get rid of the labels here. Okay, so I bet that that is true, that that is the Cayley graph of a group. So let's try to understand that for a second. Let's see. In Humph. Okay, need help here, need help. Okay, so let's say make a 3D graph of this. Okay, so that's going to be, that's going to have this sort of tubular structure like that. I bet what we do, I think what we can do, if those are kind of non-commensurate, okay, let's try something like this. Let's try n plus 4, n minus 4, n plus 7, n minus 7. Okay, so I reckon that's going to make something which is kind of like this tube type structure. Okay, so that's going to make a tube. So interestingly, that tube looks to be the same tube. There it is. Looks like one of those carbon nanotube things. Okay, so that tube, the question is, does it make any difference that we have the inverses there? Because those inverses, I don't think it does. I think those inverses don't make any difference because those inverses are just making double edges there.
Yes.
So
you also asked the tube circumference. It's 4 squared plus 7 squared, square root of that.
Yes, actually, you know, I was showing this thing to some one of my little hobby things is teaching computational thinking and other things to fairly young kids, and I was I thought this would be a good example thing to show, and so one actually high school age kid, she very quickly figured out the same thing that you figured out, that thing is a square root, but let's go through actually why that's true, let's see. You had sent some mail, I think, Ed, with some explanation of this. Let me pull that up.
Yes.
The tube circumference. Okay, this is Ed's tube circumference analysis. Did you save this in the Dropbox or not? You didn't, I think. Okay, so let's take a look at this. Oh, nice. All right, so what you've done here, so this is the n plus 4, n plus 7 tube. And what the heck is that? More editable. What do you mean by that?
I wanted to move the points around so I could see what was going on, and that's the second or the third picture in this.
How do you move the points here?
With Grassplot, you're able to move points around.
How?
Might have dropped in 12.1. You can do it in 12.0 though.
Oh, the crazy Java applet thingy. Is that the thing?
Right.
It'll be back, but okay. All right. So what you're saying is, okay, yeah, I've seen something like this. So what are you doing here? You've got, what is this now? What did you do here? So, I mean, it makes a grid. I mean, I think I had that in my blurb here. You get, for a while, you just get a grid. And then at the LCM of 4 and 7, you get it joining up, right?
Correct.
But so you have a better representation of that. What are you doing here? What's this? Is that the unraveled version of that?
Yeah, that's the flat version, because I wanted to see what was going on, and then I made the tube again and just basically made a slice through it. And it wasn't until I saw the final picture that I figured out what was going on.
Right. Well, this, whatever she is, 15-year-old or something, was ahead of you. But okay. So let's understand this. So if I label this, if I say edges here, so presumably on this, do you have genuine vertex labels here? In other words, are you labeling this with the correct values?
Yes, yes. Basically, 1, 1 is at 1, 1, and so on.
Oh, but why is there a 1, 1? Why are there two numbers here?
Oh, those are the coordinates. The vertices are the coordinates.
But what is the value in the original iteration? What's the value that should be assigned to each of these points?
Oh, this is this. That's the same thing.
I don't understand that. Look, here, right? If I take this, I've got a single number, n, at each point.
Oh, right.
What is that n at each of these points?
I didn't do the mapping back to the original first graph. I did the equivalent, semi-equivalent graph with the grid.
Okay, but let's do that mapping, because what you're basically showing me here, this is going to be a way of understanding, this is basically a torus that's being constructed, right? Because what you're saying is this whole thing is a one-way square, and it's being connected by this two-way thing, right?
Right.
And so what you're saying is, I don't understand why this is an n plus 4, right, here, but what's this thing here? Do you see what I'm saying? There should be an n plus 4 going. Why are there two things going?
Yeah, this is a different graph. It just looks similar.
Wait a minute. Is it an unraveling of this graph or not? Do you understand what I'm asking? I mean, so this graph is the graph from the iteration, right?
Correct.
Is this graph the same graph, but with just a different rendering?
No. There's some more noise, some more two vertices and things like that in the original graph.
Okay, well,
I can do the full mapping.
Let's figure that out. Right, let's figure out what it should be. I mean, so in other words, okay, so now explain your understanding of, I don't understand this.
So in this tube right above, if you go through 2, 7, and 4, 4, you get a slice through the tube. And basically, I also figured out what edges would be sliced. And when I approximated all the points in one slice of a circumference, I got the picture at the bottom. And then it was clear that the circumference basically followed the same distance as one of these diagonals.
Okay, I want to understand this, but also, according to my high school age informant, she claimed that you have to divide by the GCD.
Yes, you
do this. But okay, but I mean, I want to understand this unraveling, and there should be a way of labeling every point here. If this is the same connectivity, you're saying this is almost, because what we're seeing is, if we do just, so which one gives a pure grid? Can we get something, okay, before we reach the GCD, we will get a pure grid, right? I'm sorry, before we reach the LCM, we'll get a pure grid. Am I making sense?
Yes, with say you used 4 and 8, basically that would produce.
No, that would 4 and 8, it'll degenerate into nothing. Okay, what we want to do is we want to use two relatively prime numbers that are, let's say, I don't know, if I use 9 and 17 or something, it'll go for ages just as a grid, right? Until we get to the LCM of 9 and 17, it will be a grid.
Right? Correct. Mm-hmm.
Okay, so what we want to write down then is, so in that grid, these vectors correspond to, so let's see, what we're getting here, and in fact, I had figured this out last night. Let me show you something, and this is now, okay, and we're going to talk about causal invariance. We're going to talk about the continuum analog of causal invariance in a little while here. Okay, but what I had figured out, where did I put this? Help. Oh, it must be up here. Okay, here we go. All right. Okay, so let's consider the case n goes to n plus a, n plus b. Okay? And Jonathan, if you were going to pay attention sometime, this would be a good time.
Okay.
There. Okay. So what we're doing then is we're saying, let's imagine that this was the symbolic n plus a, n plus b. Okay? And I've got this code here. Okay, so what this is showing is which branch number. Okay, the ones and two. You understand the notation. This means go down the one branch and then the two branch. This means go down the two branch, then the one branch. Right. So a plus b you can get to by going either down the one branch and then the two branch, or the two branch and then the one branch. Right. It's commutative. Makes sense. Ed, are you on board? Do you understand this? Do you understand?
Yes.
Okay, so our mission here is which of these branches are going to be coincident? Okay, where do we get mergers? Right, and those mergers will correspond to, given a and b, we need to find all those integers, p sub I and q sub I, for which p sub I times a plus q sub I times b is equal. Do you understand the question?
Yes.
Okay, what's the answer? Is it related to extended GCD or anything like that? I don't even know how extended GCD works. But is it related to the Chinese remainder theorem? What is it related to? How do we figure that out?
We can just try testing it. If for the 917 graph, try putting in like 30 or something.
I know how to work it out. Look. I mean, if we say, you understand, it's going to work. I want to know what is the mathematical way to think about this particular thing, right? It's a Diophantine. It's a simple linear Diophantine problem.
Right. For that one, it's the Chinese remainder theorem.
What's that?
For that one, it's the Chinese remainder theorem.
Okay, well, so what is our function for Chinese remainder theorem? That's we don't call it
least common multiple, I believe.
No, it's just Chinese remainder. So
okay.
Okay, so let's understand how this works. So the Chinese remainder theorem that satisfies all the integer congruences, x mod n equals r mod m. But how do we use the Chinese remainder theorem for this?
Remainder 1, I believe.
I don't understand. Ed, you understand what I'm trying to do? I'm trying to find out for given a and b, right? So what we're going to do is we're going to generate table p times, let's say a is 4 and b is 7. Okay, so it's 4b plus 7q. Okay, we make a table of that. P goes up to 10, q goes up to 10, right? Okay, so which numbers here are duplicates, right? So if we say, counts a flatten of that, right? Our mission, and then we want to say select hash greater than 1, right? Derive those numbers. Where do those numbers come from? Do you understand what I'm saying?
Mm-hmm.
Right. So those are the numbers that correspond to places where there was more than one way to get to a particular value here. Now, why isn't 28 in here? Am I going crazy here? Why isn't shouldn't there be a value for which, why isn't the LCM in here? Do you understand the question? Jonathan, do you understand the question?
Yeah, but I'm wondering why it's not just Bezo's identity. Sorry, the answer to your previous question.
I don't know, because I don't remember what Bezo's identity is. Would be a good start. I mean, I'm sure it's something elementary. What's?
Well, so in the two variable case, it's saying that a1x1 plus a2x2 equals d, where where d is the greatest common divisor of the a's. but it represents the general form of the Diophantine equation for which the extended Euclidean algorithm is the solution.
Fine, but then so what? But okay. So what are you saying the answer is? So P sub I.
So for the case where, yeah, for the case where P sub I A plus QIB is equal to the GCD of A and B.
But I don't want just that case, but that's a good start. Yes.
But once you know that case, then Bezos' identity gives you all the cases, because you can just multiply things.
Okay, that's clever. So,
once you have one solution, once you have one pair of Bezo coefficients, then the Bezo identity gives you the set of all.
Okay. All right. So then, if I do extended GCD of 4 and 7, I'm getting 2 minus 1 there, right?
Right.
And are those the coefficients that you're talking about?
Right. I believe so. I don't know exactly what extended GCD is returning.
Okay, so extended GCD is returning a list where.
Yeah. Okay. Yeah. So the R1
it's
N1.
the remainders.
Right.
Well, it's the R1 R2.
If you have a pair of coefficients X Y. Actually, I may misremember this. It might be easier if you look this up. But okay. It's something you take X plus something over the GCD, and you take Y minus the something over the GCD.
What is it called? Bezos? But I thought Bezos' formula.
Bezos' identity, or Bezos' lemma.
Formula is something different. It has to do with multiple. All right, let's see what Wikipedia has to say about this one.
Oh, the reason 28 didn't work is you didn't include 0. It was the LCM.
Okay, all right. Okay. Using extended, all pairs can be represented.
Right, so extended GCD is giving you one pair XY, and then Bezo's identity is telling you how you get all pairs.
Okay. Let's understand what that is. Okay, so then.
Yeah, so for any arbitrary integer k, you just you take one coefficient, add k times b over the GCD, and take the other coefficient and subtract k times a over the GCD.
Okay, sorry. So let's take these coefficients. So we're just basically taking. So for all. Wait a minute. Which one is the k? Is it a one parameter family or a two parameter family?
Is what a one parameter family?
The set of solutions. No, I know, but are these A's and B's the same as my A's and B's?
Yes. Yeah, they're your 2, 3 or your 4, 7 in those two examples.
Okay, so fine. So then this is the list, which is for this. So K, this one is 2 minus 1. Where's the 2 minus 1 coming in? Those are the X and Y's.
Yeah, exactly.
Correct?
Yep.
Okay, so then what we want is extended GCD. Okay, so what we want is last of extended GCD, which is the X and Y, plus K times, so it appears to be BA over GCD of B and A, right? A and B, correct?
B minus A.
B minus A, thank you, yes. Okay, so this would be AB here. So this is our formula. So now we say with A equals 4, let's say, B equals 7. And then this should give us this. Okay, so that claims to be a family there of, that claims to be a one parameter family of solutions here. Okay, so let's take a look here. And let's start this with, what do I want to start with? I want to start with 0 here, you say, Ed. Okay. So now you're going to tell me that this is as a function of k. So I want to say table k goes up to 10, for example, that thing. What happened? There are 2 numbers there. So what are those 2 numbers? Those are the coefficients of A and B. Is that correct?
Right.
Okay, so we want the dot product of that with AB in general here. So we want to say map AB dot that onto this, and that should be giving us, but actually already this is a useful thing, but I want to see this. Splat, what happened here? Dot, what happened? Those were lists, right? What did I do wrong here? Help. K goes up to 10. Okay, that's a list of lists. Oh, I see what's wrong. I see what's wrong.
You should put it outside the table.
Yeah. So actually what I want to do is put the table in there. And conveniently, it's reddening itself. K up to 10. Get rid of that. Something went wrong here. So let's take the original thing again. Okay. So this was, you claim those are the offsets. Oh, but I don't have negative numbers. My AB never gets negative. So something's wrong there.
Also, wait, why is this incorrect? You want them all to be the same. That's the definition of the problem, right?
No, I understand, but I don't want them all to be equal to 1. I want them to be equal to whatever values they feel like being equal to.
Right. But then you can multiply by any integer, and you can get whatever.
Okay, but I don't want negative numbers there.
Fine. Okay. That is an issue.
But so these are the numbers for which. So if I go up to like 100 here and I plot these. Okay, so they lie on that line with some approximation. There'll be some wiggle around there because why is there no wiggle? They're actually in an integer ratio. I mean, they're in a same rational ratio. Okay, how do we deal with? Okay, so first question is, how do we deal with the negative numbers? Right, so those are you see what I'm saying? I mean, those things are solutions for which give value 1 on the right-hand side. And you say we can multiply that by anything, right?
Right.
So like our friendly 28, we can't multiply by anything. We can't, because we already know these are the only possible numbers that appear on the right-hand side, right? See what I'm saying? So the first question is which numbers, it's a chicken McNugget type problem, right? Which numbers can appear? Am I making sense? Ed, do you have an idea of this?
Yes, and that's also the Frobenius function.
Right. So how do I use that's what I also figured that one out. So Frobenius solve gives all the solutions to the equation a sub 1x IC. So this should just be Frobenius solve of, this should be those B's for which this has a solution, right? Right? This should be this. If I say this 47, and then I say 39, for example, here, then it will give me that value, right? It'll give me the two things that solve that.
Right.
Okay.
And with 28, you'd see zeros.
Right. Okay. So Frobenius number, I think, might be the number of let's see.
So that's the maximum number that you can't construct.
Right. That's the missing value.
But are you claiming then, okay, so if I chicken McNugget this, what's going to happen here is that after a while, I'm going to be able to construct every number here.
Correct.
Correct?
Uh-huh. And Frobenius number will give you the last number that can't be made.
Okay. All right, so that's interesting. So then there, okay, so after a while, okay, so 17. So then what this should say is that if I pick these, okay, so what that means is, what does that mean for this multi-way graph, right? That there exists, after some transient, you can reach every number in, well, that just says you can reach it in one way, right? This says, so what does it say about this graph? So after a certain number of steps, certain transient, every number, every value can be reached by the iteration, right? But what does that tell you about the multi-way graph? But now, how many times can it be reached? See, I'm a little confused by this picture, right? Because this picture seems to say each number can be reached twice. Am I making sense?
May as well change that one to 4, 7.
Okay.
Since we're more familiar with those numbers now.
Okay, so 4, 7, 4 and 7 a branch, 4 and 7. Oh, I see. This is just commutativity. The reason for this grid is just commutativity, right?
Right, and 28 is the first number. 28 at the bottom appears twice.
Well, it's just commutativity, right? But then what's going to happen is, if we continue this longer, right, then what we will see is that the 28 has another, and that's your thing in your twisted commutativity. Let's just use the spell checker. So what this is saying is, if I continue this to 7 steps, okay, then I break the grid, because 21, I don't understand this picture. So everything has 2 paths because of commutativity, right? But the claim is that 28 has more than 2 paths, but I'm not seeing that here yet. Am I making sense?
28 appears 3 times in that graph.
What do you mean? Where?
On that, oh, that's a 23, sorry. 28 does appear twice, though.
I don't think so. Nest graph wouldn't do that. Well, we can check that by using the Multiway System code. Let's see. Where did I have that code?
28 should appear twice, as well as having 2 arrows going into it on both occasions, right? Because 0 times 7 plus 4 times plus 7 times 4, and 0 times 4 plus 4 times 7.
Yes, but this is a states graph, and why shouldn't it combine those states? Or am I being confused here?
If it's a states graph, then it should.
Well, let's understand what happened here. So first of all, I need to go find, what was I calling this? Numerical multi-way function. I know what I was calling it. You didn't happen to improve that code, did you, Jonathan? I mean, what I did there was just a complete hack.
No, I didn't modify your code.
Okay. It's absolutely grotesque. Let me just pull it up here. Multi-way function system. Okay, so this code is utterly grotesque. And in fact, if we can figure out, you can pick this up, but if you can figure out how to improve this, this would be, I mean, this is using that ridiculous combinator hack, which I just cleaned up to the point where it would work, but that's about it, okay? So this would be multi-way function system. And then I give the function, and then I give t and u. No, I give init. What the heck is u? Oh, I know what it is. That was really stupid naming of mine. But so this would be states graph, right? States graph structure. Okay, so the question is that it's the same. Okay, so this is a states graph. So if we label that states graph, right, that means there is no repetition in there, unless something went totally wrong here. Okay, so why doesn't 28 have more edges coming into it? Because it can be made in two ways from the root. So maybe the reason is that there are simply two, well, let's just not be confused. Let's just try running this for another, you know, let's say 10 steps here. Oh gosh. Let's try a simpler case here. Let's try 2 and 3. Okay, so 6 should be, okay, so there's 6, right? 2 and 3 goes to 6. How many paths lead to 6? Two and 3 is, okay, so this is the 2's side, goes down there. And this is the 3's side, goes down here. But we're not seeing two different paths here. We're still seeing, that's still just the same. Oh, this is 2 plus 2 plus 2, which has no commutativity story, right? Because these are identical, it has no commutativity there. That makes sense? Get it? No? Okay, look, do you understand what I'm saying?
Who are you talking to?
Both of you.
Well, yeah, I understand.
Okay, so there's only two paths getting to 6, which we, whereas in terms of indices, what we're seeing here is...
But there aren't only two paths leading to 6.
Okay, explain.
Well, if you include event instances, you'll see there aren't.
Okay, let's take a look.
I think.
Oh, 28 does not appear twice. It was 29 instead.
Yeah, I know.
Okay.
What are you saying? Include event, what is it called? Include event instance?
Instances. Oh, maybe I'm wrong. But there are 4 ways to come out of 6, which is not what I was expecting.
What I was expecting either. So let's walk through again. So it would be really good if we could label these events, right? So this event is an add 3 event. This event is another add 3 event, right?
I mean, we can label the events, obviously.
Okay, well, let's maybe we should do that. But let's just trace this manually for a second, okay? So this is the add 2, the add 2, and the add 2 event. So the point is, normally we wouldn't have been able to reach 6. Yeah, look. The point is that, for example, we can reach 7 in 3 ways. So let's check that. Okay, we can reach 7. It claims the total number of paths to reach 7 is 3, it says, and that's correct. See that?
Why are we not including state path weights?
Well, we could do that. What's it called? Include state path weights. Is that right?
Mm-hmm.
And how do we display them?
Vertex label goes to...
No, edge label.
Or, well,
path weights.
Vertex label goes to vertex weight.
But then we'll not see the numbers here. Can we do name and that?
I don't know.
That is unhelpful.
Now it's just showing.
Okay, let's see vertex weight again. Yeah. Okay, so those are mostly ones. Well, we don't remember what thing, so we're going to have to do this more carefully. So how do we get vertex label? We have to pull out the annotation there. Am I making sense? Do you know how to do that? Okay, I have a complete graph with annotations. Okay, so now how do we use the annotation value? Great. Where are the annotation values? This is not what I want in this documentation. Let's see if we can find Charles. Yeah, this is cruddy documentation here. Okay, annotation value of G . All right, but in any case, let's try to understand what happened here. So these are the path weights. We don't know what that value is there. We can clearly do this. Kind of a hack, but we can clearly do this. We just map this over automatic and vertex weight, and we'll get two parallel pictures, which we need to make bigger. Oh, come now, they can't be different heights. Why are they different heights? Okay, no matter. Well, we can do this. Okay, this is the vertex weights. These are the values. Okay, so what we're seeing here is that 7 has vertex weight 3. But that was a pure grid-like vertex weight. Am I making sense? This is a deviation from the grid vertex weight. Do you see what I'm saying?
Mm-hmm.
Okay, because there's a vertex weight that we get if there was purely a grid without any extra edges. So that's what Ed was showing earlier, right? Ed?
Yes, my dog is barking at me.
Oh, well, see whether it agrees with you. Okay. Okay, so what we're trying to understand is these things where there are these essentially coincidental additional connections, right? Here. Okay, so I'll tell you a result that I think I have is, so we need to understand these. We need to understand what the number theory of both, what the additional values that are beyond what you would expect just with a grid are, okay? But the place where this is interesting is, so first result is, I believe that these 3 cases are all causal invariant. All those 3 types of multi-way graphs have causal invariance. Isn't that interesting?
Hello.
Hi, Charles. All right. We are grappling with really cruddy documentation for annotation value. This is really if I might say so, awful.
It's the first version.
Ha!
And it came late.
What's that?
And it came late in the, we changed the design last minute. So
okay, well, anyway, you can do better. But okay, so my question is, how do I label this? Will the vertex labels show both the name and the vertex weight? Do you understand my question?
Yes. So both the name and the weight. Right. So I think if you put place, name, and
I just want to put them in the list. Just let me put them in a list. I want to put the two things in a list. So I want vertex labels to be, and I tried the obvious thing of name, comma, vertex weight, and it didn't work. Right? You understand what I'm saying? This didn't work, even though I would have expected it to work. Right, that just picked up the second value, the vertex weight value.
Right.
So how do I use annotation value to get this right?
So here we want to actually draw the graph and extract that. So if you do vertex label goes to placed, and you keep that list, comma, I think maybe top and bottom in a list.
Oh, that's crazy. Brilliant.
No,
I would say that
vertex
didn't
weight.
work.
What? Sorry, I want to. Is the graph weighted?
Yes. As you can see, those are the vertex weights on the right. I thought this part was going to be easy, guys. We're about to get to something more interesting. I wanted to get through. Okay, so by the way, is it obvious to Ed or Jonathan why in these cases you get causal invariance in each case? I mean, it might be something to do with some group property of these mappings. Because I think what's going to happen, I mean, what we're going to work on is the continuum limit, in which we're going to be talking about, the injectivity of certain mappings. I don't know whether this is related to that.
I think the key is the Frobenius problem. Eventually, there's all numbers appear, and so you basically get a grid structure with n plus a, n plus b, and the wrap grid structure is based on the larger of the two values.
Okay, so hold on. So, somebody was asking what was going on here. Just explain. We're looking at multi-way systems based on numbers. So at every step, we're taking the number n and we're replacing it with two vertices. So the number n is replaced by two vertices, in this case 3 and 4, and we're showing the graph of what comes out from that. I mean, honestly, it's one of these kinds of things which I would have expected somebody would have investigated at some point in history, but who knows? I know I looked at this. There's one note in NKS about this, but that's it.
Well, Frobenius.
Well, he didn't draw these graphs.
No.
He probably existed before graph theory was a thing. But
correct.
Okay. But so he was dealing with this particular case. I mean, we're going to deal with many more functions here. And yeah, there's an interesting point from Richard on a live stream about symbolic expressions. Yes, interesting discussion. Let's come to that in a minute. The question of isomorphism for the symbolic expressions, which is non-trivial. And I want to look at that. I mean, for the case of arithmetic, clearly isomorphism is trivial, but that's one of many directions. There's non-trivial isomorphism there. Another direction is the infinite limit and its relationship to transfinite numbers, and we'll also come to that. But right now we're stuck on something much more elementary, which is displaying these graphs. Charles, your thoughts?
Which part? The labeling?
Yes.
Yes, I'm working on it. There is something I missed.
Fine.
I will find it.
All right. I thought this was like one of these things that was totally trivial, and I just didn't read the right part in the documentation, and the documentation was kind of awful. Okay, so this is in the category of not so trivial. Okay. Okay. Well, let's come back then to Ed's claim about Frobenius's results. Okay, so your claim is that as soon as we get above some value, so the basic point is, I would like to keep my summary here separately. Let's put my summary in here. Okay, as soon as one is above the Frobenius, what is that Frobenius number called? Is it just called the Frobenius number?
Yes.
Then every possible value must occur. Then every possible value
Integer.
Integer value, yes, must occur, and every positive integer, non-negative integer value must occur for this quantity for some p sub I and q sub I. Okay. Okay, so what? Why does that force us to have a grid? Why does that make it obvious that it's a grid?
It basically acts like a grid equivalent to the larger value, and you have with wrapping based on the smaller value.
Claim is that there is then a grid. Why is it based on the larger value? Show me that. I mean, with wrapping based on the smaller value. Really?
Mm-hmm.
Okay, so let's see that. I mean, I'm sure something like this is true, but let's just see it. Okay, so what you're saying is, if I look here, so that's 4 and 7, okay? And the Frobenius number for this is 17, is that correct?
Correct.
Okay, so you say above 17, that's 17, where does 17 appear?
It doesn't.
Oh yeah, it doesn't appear, right. So above 17, so 18 is the first thing that appears there. So above 18, you say, so that's an interesting claim, because what we're seeing here is at 21, I don't understand. Okay, so what is your comment about wrapping? So again, how would I do something which doesn't have wrapping? Would I have to have, is there any way to make the wrapping, what is the highest Frobenius number? The wrapping will not start until I have a Frobenius number, basically.
Right. If we started with a grid 18, 19, 20, we put those in each column with 7 values and continue on to infinity. Basically, the pattern you would see in the arrows would be repeating after 18.
Okay, so wait a minute, wait. You're saying which numbers?
If we did a grid starting with 18, 18 to 18 plus 6, and so on.
Oh, you start at 18, right? So there's 18. I see. So that grid you claim the grid. Now, when does the grid repeat again?
Every 7 values, and it's not starting with 18. If we went, I'll make a picture and I'll send it to you.
Well, I want to understand this. I mean, okay, but you're saying that what's going to happen is, as soon as so with respect to these path weights, what is the distribution? Can we compute the distribution of path weights, for example, that we get here? How is the distribution of path weights determined by A and B? How about you figure that out, Ed? That would be offline, okay? All right, if Charles knows how to do this, let us know. Otherwise, we're going to move on to the next thing. Okay, so again, is it obvious to you guys? So let me tell you the results that I have, okay? It appears to be the case that these cases are causal invariant, but this case is not. Okay, and in fact, an bn plus 1 works only if a equals 1 or b equals 1. So this is a bunch of Diophantine equations, basically, 3n plus 1-ish, so to speak, because it's some number of copies of this and some number of copies of this. And they don't commute, right? Those functions don't commute. Or am I being confused? Do you understand my question?
Yeah, clearly they don't commute.
Okay, so what we'll have is each one of these. So we could have a bunch of identities. We basically have index identities that say that the sequence of indices, whatever it is, this sequence of indices give the same results as some other sequence of indices. So in this case, where was it? Okay, so if I look at, what is this case? This case is 3n, 2n plus 1. Okay, so that's a case that I claim is not causal invariant. Okay, never. So you can see that there is some merging here. If I go to like 12 steps, I maybe should just use nest graph. Okay, there we go. Got rather beautiful. Very nice decorative object. And you can see there's some merging, but there's not enough merging to give causal invariance. Okay, so what we probably should do is to look at, as a function of a and b, we should be able to see the rate of branch pair convergence as a function of a and b. That seemed like a worthwhile thing to do. I mean, right. Let me explain the bigger picture here. So the first thing I want to do is I want to try and understand the space of causal invariant systems within these integer multiway systems. The next thing I want to do is to start looking at non-integer multiway systems. Okay, so what's our way of looking at branch pair convergence as a proxy for? Okay, so what we want to do here, I think I had it well. Okay, so I can just compute. If I go someplace up here, I could compute here this thing. Well, let's see, what was it? It was 3n, 2n plus 1. Okay, we got this, and we want to look at branch pairs. So that's the states graph structure, right? It looks a little weird, is that right? Okay, let's go a little bit more. Yes, okay, so it has some convergence, but not very much. So now if we look at branch pair, what do we want to look at? What is it called again? Branch pair.
What are you trying to find? The resolutions list or the list?
The list with unresolved and resolved.
Resolutions list.
Branch pair resolution.
Branch pair resolutions list.
Okay, so that shows one resolution of a branch pair there, mostly unresolved branch pairs, right? So what do we have? What is our way of assessing the rate, the extent of causal invariance? So in other words, if we were to look at the corresponding thing for something that we believe will resolve, that is 3n, n plus 1, for example, okay.
Right. Obviously, the coarsest approximation is just to look at the ratio of the length of the lists of resolved and unresolved pairs.
But this one, if I ask for causal invariance in this case, right, I'm going to say causal invariant Q. Okay, do we believe that result? So that would say that any unresolved branch pair here resolves after a fixed number of steps, right? How many steps does it try?
So if you determine causal invariance up to step 6, then it looks at the unresolved pairs after 3 steps and determines whether they've resolved up until.
Okay, so this is a reliable true for causal invariance for this case, yes?
Well, I mean, as reliable as it can be as a finite procedure.
I understand, because the general problem is undecidable. But so should I test it for successive t?
That would be useful. Yeah.
Let's go ahead and do that. Is there a way of doing this without me trying to do this in parallel for many of them? That's really weird. Why does that happen?
So that means that there'll be branch pairs after 2 steps that hadn't resolved by step 5, but which obviously had resolved by step 6. So we're okay. Okay.
All right. So then the question here is, as a function of a and b, right? If we're looking at a n bn plus 1, for example, we should be able to see. Well, actually, the more general form. Look, the general form here, and we could ask for sort of group theoretic properties of this, is an plus b. So the general form is an plus b, cn plus d. Which looks awfully like one of those, you know, for real numbers or complex numbers, we're going to end up with a Möbius transform. You know, this is the world of things like, well, it's like some kind of. There's some nice mathematics for the continuous case, but I don't know for the discrete case. Richard on a live stream is commenting about things to do with the 3n plus 1 problem, that's generalizations. Yeah, that's correct. And we can look at some of these contingent things. I mean, there's a pretty good example in the NKS book of, where is it? It's a pretty good example, as I recall, of, yeah, let me show you an example here, if I remember correctly, of the case with numbers. Yeah, there it is. This is the proof, basically, that you can emulate an arbitrary cellular automaton with a generalized 3n plus 1 problem. Oh, this is emulating a register machine. Sorry, that's emulating. That's showing that you can emulate that with a generalized 3n plus 1 problem. You can emulate all kinds of things.
Right, but the remarkable result that Richard on the live stream is pointing out is that you can also emulate oracles, which is not at all obvious.
That's not at all obvious and rather interesting.
So hang on,
I see. It's pi2 complete.
Yeah,
wow.
I just linked to a.
Who showed that? That's the non-trivial result.
Yep. Well,
is that the thing? Because I don't remember that being a thing. Generalization, okay. Is pi2 complete?
Yeah, so
hey,
if
is Matthew on our live stream? Matthew is a pi2 enthusiast. Matthew.
I'm here.
Did you see this thing? Explain this.
Give me some time to think about it.
What does it mean to be pi2 complete? What would be
just you have to give me some time to think about it.
All right, okay, fine. And I don't know what the 0 means in that pi2 designation. Oh, does that just mean no? Pi2 means a bunch of exists, yes?
The 0 just means it's over the integers. You're quantifying over the integers.
I see. But the 2 means quantifying over 2 levels of functions?
2 alternations of quantifiers.
Oh, so for all there exists.
Yeah, it's for all there exists.
Oh, two like that.
Yeah.
Okay, you can tell us when you figured out what that means.
Right, and so I should mention the generalization of the problem that they considered in this particular paper is the case where you have AIN plus BI mod P.
Right. Yeah, that's the case. That is the case also in the NKS book. Oh, Ed has something here. Okay, so Ed is showing us. What is Ed showing us? What is that, Ed?
After 17, it starts repeating.
What is this object that you're showing?
This is the original nest graph, but arranged so that the vertices are on a grid based on the larger.
Okay, that's exactly what I wanted. Yes, yes. So you say this is isomorphic to the graph. So if I take that nest graph, oh, you proved it's isomorphic because you just changed vertex coordinates here.
Right.
Okay, so let me understand this. So this overall grid is what? That's a grid of adding sevens.
Right.
And these are the different ways to add 7. Okay. And the adding 4s are these cross connections here. This is nice.
Right.
Well done. Yeah. Okay. And where's the Frobenius number living? The Frobenius number is the fact that this isn't all filled in. Is that right?
Correct. With 17, the last missing.
That's cool. Okay. So then if I were to do this in, let's try it for 2 and 3, for example. So you claim here 2 and 3, and then quotient there with 3. I see. Very nice. Very nice. So that's an explanation of what's going on here. So this is also showing us, in terms of branch pair resolution, does this show us obviously that it's causal invariant? Yes, I think it does, because it shows us that for every path here, we can always get back.
Right. I think after 17, you can be pretty sure everything's going to act predictably.
Okay. If I were multiplying instead of adding, would I basically have the same results?
I don't know. I would have to look.
Okay, all right, but that basically resolves the question of the addition. Good. So, but this case, the 3n, 2n plus 1 case is more complicated, because that case is going to be, you're making a choice at every branch, you're making a choice whether you use 3n or 2n plus 1, and the question is, where do those agree? And the answer is, those agree only on this rather thin, wherever it was, on this fairly thin set of places. So that's the choice, that's the 3n, that's the case of, that's the n plus 1. Okay, that's the 2n plus 1 case there. Right, so this is saying that most of the time this doesn't converge. Okay, so what we want to do, we're going to look at convergence rates here. So let's go ahead and do that for an plus b, cn plus d. Okay, well actually, first thing we could do is just find out which of those are causal invariant. So do we start from 0, do you think? Do you think that's the best thing to start from? I want to delete that picture because it's too big.
Yes, I'd say so.
Okay, so this is an plus b. So this is experimental math in action. We could try and figure out a theorem, but that would take us a long time. Instead, we are just going to compute. Okay, so let's go ahead and make this a parallel table of that. Let's say A goes up to, let's just do A up to, how many do we want? We want 4 to the 4 is civilized. So we want A up to 4, B up to 4. We might try negative numbers as well, but we haven't done that yet. D up to 4. Okay, who's going to predict what this is going to do? So this is going to make us, this is going to figure out for which A, B, C, and D this is causal invariant. There's a, oh, I see. There's a Quinn on our live stream is pointing out that this pi02 completes, pi20 complete set. It's a set of Turing machines that compute total functions. I see. I see. That's so it's basically just saying it's all possible. So, oh, this is really a statement. I see. So that what that's saying is, well, we'll wait for Matthew to come back with this. But I think what it's saying is that because this thing is universal, is capable of universal computation, its halting problem the family of halting problems is in some sense complete. That is, any halting problem you want, you can, because you can encode an arbitrary computation in one of these systems, any halting problem that you care to ask can also be encoded.
That sounds correct to me.
But the statement of completeness is, how could you be pi 2? You could be in pi 2, but you could also be in something much lower than pi 2. But to say it's pi 2 complete, let's take a look at this. Okay, let's find out where the, so the claim here, so let's find out where the truths are. Okay, so this is going to be the, oh wow, that's funky. So this is the set of, this is the claim for the set of ABCD things which are causal invariant. So this gives us a density. So if we say length of this divided by 64, 256 rather, silly me. That's telling us that 40% of those systems with this way of estimating causal invariance are causal invariant, including some rather exotic ones. I mean, let's look at the most simple-minded exotic one. Let's see what we're nothing. Okay, the 1, 2, 3, 4 system. Let's take a look at the 1, 2, 3, 4 system. Okay, so the 1, 2, 3, 4 system will be, let's just do this. Nest graph of, let's pick one up from here. Where is it? Nice one. Ag. Okay, very trivially. So this is saying nest graph of 1, 2, 3, 4. So that is 1, A, 2, 3, 4. So this should be, so the claim is this is causal invariant. Oh my gosh. You know, it is just crazy how complicated these things get so quickly. So quickly. Oh, that looks just like the Fibonacci one. Okay, so let's take a look then at the ones that, let's take a look at the nest graphs for the ones that say that they are causal invariant here versus the ones that say they're not causal invariant, and see whether it's obvious. Well, actually, what we could do is just make for ABCD, yeah, let's just do this. Let's just make those for, at least we just go up to 3 because it seems like nothing exciting happens at 4, so that'll make it easier. Okay, so let's do this. Let's say nest graph of this, let's say parallel table, nest graph A times this plus B, C times this plus D, up to 10. And let's go ahead and make that table, A up to 3, B up to 3, C up to 3, D up to 3. And let's not make the mistake of not labeling the thing. Let's say labeled, and then let's put ABCD here. Okay, let's see what this looks like. And let's actually make these image size arrow tiny. Okay, so this is going to claim to be, so the question now is whether this may be disastrous, because it may be that there's some really huge ones, but when I go up to 10, but let's just see what happens here. So remember, what this is doing is this structure of graph seems to be sort of characteristic of a causal invariant system, whereas the structure of graph that we had earlier, which had a much more, oh, that's a good sign. Formatting, formatting, formatting. Okay, there we go. Okay, let's look at these guys. Okay, so let's try and classify what's going on here. Oh, we should have marked which ones are causal invariant and which ones are not. Okay, so like 2, 1, 3, 2 looks like it's just a perfect grid. Wow, look at this, it's so crazy. Okay, so there's several different categories here. And let's try and mark on this picture How do we want to do this? I want to take the ones that are causal invariant. I want to take this list here. Oh, sigh. Well, I'm going to be very, is there an obvious way to take, yes, there is, to take just the, so line 444, we want to take, no, I know what we want to do. I know what we want to do. What we want to do is we want to take this list here, %445, and we want to say select %445, any true, all true, hash less than 4. Okay, that's the case of all the ones that we found as being causal invariant. And so now what we want to do here is we want to say map at on map at %450 with this list %451, and now we want to say there, let's say framed hash background arrow light yellow.
Seems to be the boring ones.
Okay, well, let's find out. Okay, so here we go. So this is going to show us the causal invariant ones. Okay, so those are all causal invariant. So 2122 is not causal invariant. 2131. Okay. Why is 3221 a pure grid? And why is it obvious to you that these Fibonacci, that one gives the Fibonacci thing? It's one of those typical, I mentioned it in the NKS book, and it's one of those typical things where I just say the result is blah, and I have no idea how I derived that. But so these ones here, for some reason, boy, what is the criterion here? What can you see? What's common to the ones which are causal invariant versus not? So, I mean, I can see in this picture what they look like, but, and also there's a question of whether some of these are causal invariant, but just take a while to resolve. Like, let's say 3122. Let's try 3122 and let's look at our branch pair resolution rate for 3122. Where was that? Okay, so here's 3122. Jonathan, is there a way to tell it to show us by successive steps which branch pairs resolved, or do we just get to say at a particular step which branch pairs resolved?
So you can get branch pairs. Well, obviously, branch pair resolution list tells you up to a particular step which one's resolved. You can also ask things like branch pairs new to see which ones got produced at a particular step. But because multi-way system always takes a step number.
Okay, but so this is showing resolution rate. So let's just generate these for up to some value. Okay, so let's say t up to 7, live a little bit dangerously. And maybe we just want the number. Well, let's just actually look at them. So this is going to tell us which new branch pairs there are. Okay, what a big mess. All right, so let's take a look here at, basically we just want to say length, map length onto that at level 2. Okay, so this one, there is a modest rate of resolution, but clearly it is splitting out unresolved branch pairs at a higher rate. So I wonder whether we can prove that this is not going to resolve. I mean, I wonder whether we can see anything about the rate of branch pair.
It's interesting, the rate seems to be roughly constant at 1 to 10.
That's crazy. It's crazy. All right, I don't believe it'll continue. Let's try the same thing for a few more steps. Let's live dangerously there. Let's go parallel. I mean, by the time we're going parallel, we might as well, actually, what we might as well do is let's just put in time constrained. And how long do we want to wait? Let's wait for 15 seconds. And that's, let me just go up to 12 here. We're not probably going to get very far, but we might as well, since we're just running them in parallel on different machines, it doesn't really matter. And assuming that the time constraint actually works, because it should take maximum of 15 seconds here. So much for that. Okay, but so it will be interesting to have a proof that this does not resolve. So the question would be, what is the number theoretic way of thinking about what happens here? So as we iterate A, B, C, D, we can get, I mean, the iterates here. Let's see, if we just take nest graph. Okay, the most naive thing to do, I don't even think we need nest graph, but if we just say nest graph, n function an plus b, cn plus d, and I want to talk about continuous values in a moment. We can get some more serious math in there. Okay, so we're going to do this starting with 0. Let's iterate 3 times. And then what I want is actually just vertex list here, which is going to be just the application of those functions. I mean, I'm just using nest graph as an El Cheapo way to do that. Okay, so let's look at these. So these are a bunch of polynomials, basically at A, B, C, D. And I could expand those polynomials. And what am I going to see? Whew. What am I seeing here? So, I mean, left to its own devices, there will be some merging, right? There will be grid-like merging here, won't there? Okay, so if I do this, if I say here, let's put in an expand here. So I claim that that will show some merging. And I'm wrong. Why am I wrong here? Okay, so where's the first place where this should merge? AB, isn't there something that will merge because of commutativity? Or are they all distinct expressions? Well, let's just check our understanding by doing an n plus a, n plus b. Okay, great. That's nice, actually. That's a nice picture. So that shows the commutativity in action, right? But this is, the symbolic one will never do an ed folding, so to speak. It'll never have those crosslinks, correct, guys? Okay, but so this one here, the claim is there is no identity ever. Is that obvious? It's not obvious to me. There's no identity ever that causes iterates of A, n plus b, cn plus d to converge. Well, let's take an example here where let's say c is equal to 1. Oh, that's going to make a difference. Splarf. Does it make a difference if we have cn plus 1 like that? Oh, still just a tree. Okay, math-enabled people here. Ed, Jonathan, is it obvious why this is happening? Is it obvious that you can never get this, that there are never two branches that give the same thing here?
Yeah.
Why?
Well, because suppose you've picked an plus 1 for some value of n.
Yep.
Then if you substitute that into the other expression, or even the same expression, that plus 1 is going to turn into a plus a or a plus c.
Oh, I see. Okay.
And without knowing what a and c are, there can't be any merging.
Okay, fine. But the question of merging then is essentially a number theoretic question of when can these... See, I'm trying to answer the question, why... Okay, given this, how do we predict which of these numbers, for which of these there will be causal invariance? Because 2313, if we look at 2313, for some reason, 2313 has the property that in that picture, wherever it was, okay, so here, in the case where that is 2313, it merges. Whereas in other cases, it doesn't. So what is the property of those numbers that causes the merge?
Pigeonhole principle.
Explain.
We've only got a limited number of numbers, so if you actually put in values there, eventually they're going to merge.
Nonsense. Nonsense. Look at the other cases, right? Eventually, okay, so some of them are, let's look at a case that is quite tree-like, 3132, okay? Three, 1, 3, 2.
I also posted some code that might be helpful.
Okay. All right, so look at this. There ain't no pigeons here in any holes. Look at it. And clearly that happens. If you do, yeah, this is like 2n plus 1, 2n plus, yeah, 2n plus 1 is a pure tree, right? 2n plus 1 is precisely a standard binary tree, I claim.
Correct.
Okay, so there's no pigeons here. Okay, so the question is, when do you get a tree versus when do you get something which joins up? And there's obviously some, number theoretic condition for that. And Ed has some kind of picture here. Oh, and Charles may have a picture there too. Okay, so let's look at Ed's picture. 3n plus 1, 2n plus 2.
That's just limiting the maximal vertex. So remove some noise.
Yeah, right. I've seen this. I mean, so this is right. I've drawn this kind of thing before. So what do we learn from this? So some vertices, that's what we're seeing. Some branch pairs resolve, but most do not. So the question is how to think about that. All right, I want to go on, given these, unless somebody has an idea for another function to try other than an plus b, cn plus d, which already seems to be quite complicated. I mean, I've got a couple of things we could do. We could do collections of integers, which is which will get us more 3n plus 1 like, or we can look at real numbers. I would have a predilection to look at real numbers. And here's my idea there. So, because real numbers are getting us closer to the continuum limit, what I want to look at is real numbers followed by looking at, well, you'll see. I think it's going to end up with Ito processes and things. Okay, so let's take a look at the real number case. So the real number case, what we will be doing is we'll say nestedly apply. So here, we might say, but it won't be very useful with real numbers. We could say nest, for example, we could say, let's take a look at like the inverse of a logistic map. So a logistic map will be x goes to 4x1 minus x. But if we were to say that equals x prime and we were to solve for x prime in that, we should get, am I going crazy? I'm sorry, I want to solve for x in that. Okay, so there I get my formula for the two roots of the logistic map, right? Make sense, people?
Do you need to put a space between X and P?
No, I don't. Ah, we got a comment from Tilga here. Is it the case that A equals 1 or C equals 1 or, okay, so hold on. We got a claim here, a very interesting claim about our conditions. Let's take a look, see if that's right. So let's go back and find our case where, okay, hold on. Okay, so this is, well, this is our formula here. This is our array here. Okay, this is Tilga's claim. Okay, so there's the array. Data is that. And now what we want to look at is the corresponding thing with this table. Oh, we need some. Or, parentheses, A equals C and B equals D. Okay, let's take a look. Let's just try the really go wild here. Let's just see whether it's true. False. Okay. All right. Let's evaluate this. All right. And let's now compare that to data. What's the best way to do that? Should we do a map thread? Map thread of equal. Map thread equal onto %474 and 476. Do I have to do it level 2, or is this going to do the right thing? I think I have to do it level 2. Maybe I mean at level 2. That is not what I expected. Well, let's be boring. Let's just make a table of no, we could do this. We could say array of each of those. There's got to be a better way to do this. I'm just not seeing it immediately. Onto 4444. Okay, so we got a few exceptions to this rule. So the exceptions are so these are the exceptions. I don't know what to make of that exactly. Maybe somebody can take this here. Let's for the sake of I'm going to paste this so that somebody can paste it onto our Twitch chat so that maybe that's what we're trying to explain. So this didn't quite make it. Okay, let's go back to our real number thing. Okay, so now what I want to do here is I want to say, I'm going to make a nest list of something where I say for every at every step, I want to say, for example, with this case, I want to say I make the numbers that I have. I think I want to say 1 over a 1 minus square root of 1 minus hash I guess I can use listability to just apply this, if I'm not mistaken, to my set of numbers. Okay, so this will start off as the number 1/2, let's say. And let's go 5 steps. And let's say with, say, is there an easy way to do this? We want to make graphics of map indexed of of hash 1, and then we want to say first of hash minus first of hash 2. Actually, I can just do map indexed onto that. So this is going to put those, let's not do graphics, let's just do list plot. What did I do wrong? A equals 2. Oh, silly me. Yeah, it's a little tricky. Okay, so we got to do this map indexed at level 2, and then we've got to concatenate that. I claim. Okay, let's take a look at this guy. Why is it looking like that? Why is there not something at -1? Oh, because those are very close to the origin. Okay, let's look at this plot range. Arrow all. Okay, so what's happening here, rather boringly, is we've got all these numbers and they're all just converging to the origin. Okay, so we need a more interesting iteration than this. Oh, let's try changing the value of A, because I think this is going to give us, this is the inverse of the logistics map. It still just converges to 0. Is that obvious? Do people understand what I'm doing here? Yes, no, maybe. I'm trying to get, so suggest a function that maps points on 0, 1 to points on 0, 1 and does so in a way that is, let's see, what would be 2 mappings that take points on 0, 1 to points on 0, 1? Do you understand what I'm asking?
You could do a cosine and divide.
I need 2 mappings. So cosine, I mean, I could say sine, but I don't even need to divide. I can just say sine and cosine, right? If I wanted to, because they'll both map everything in 0, 1. Oh no, that everything in 0, 1. Yeah, this should work, shouldn't it? I mean, it's kind of a weird function, but it should work. Yes, that does work. Okay, so what is this doing? This is taking, at every step, it's taking, so every step it's just taking, it's a multi-way system where, so I could draw this multi-way system now by saying nest graph, and it won't be a very exciting, well, I could draw it by using these values here. Yes, I could say nest graph of this thing here, that function applied to 0.5, 5 iterations. And now what I want to say is vertex coordinates oh gosh, how do I do this? You see the problem? The problem is that I need to know which generation number it was in. Do you get what I'm saying? Do you understand? As we go down the page, it's the generations go up, and we're trying to show the vertex coordinates as a function of generation. Right? Look, this is, it's just going to be a tree here, right? How do I make a Cantor set from this? That's the most straightforward thing to do, to just turn this into a Cantor set. What do I do in there? So if a Cantor set, I want to get rid of the middle third at every step, right?
For that, you'd use integer digits ternary.
No. I don't want to do that because think about it. I'm trying to take this. I'm not making the Cantor set by removing things. I'm making the Cantor set the Cantor set is topologically like a tree, right? So what I'm trying to do is I'm trying to take every value that I get to, and I'm trying to say, give me the two values on either side, but not the value in the middle. Did you get what I'm saying? So I think that's a straightforward thing where I'm taking each value and I'm taking like a 1/3 and 2/3, I think. How do I map it? Do you understand what I'm saying? I'm trying to take each value and I'm trying to take its, what do I take? It's not its leading digit, it's probably its trailing digit, but that's kind of weird. Right, so what's a continuous function? So the thing I'm trying to do here, I'm trying to take a continuous function of x, and I've got two continuous functions of x. And so effectively what I'm doing here is I'm mapping this thing, in this particular case, where we plot, sine x, cosine x, and instead of my values, instead of I'm saying as a function of position, let's say in this case between 0 and 1, I'm just saying this is where I'm mapping each point at this point here is mapped to this and this. You get what I'm saying?
Mm-hmm.
Okay, so my question is, what functions do I need to use? So if I use, for example, two, let's think. Did you understand? You don't understand. I'm trying to get. Never mind. Okay, this is a very uninteresting pair of functions. Let's imagine that I take a ramp up and a ramp down. So let's see, my ramp up would be from 0 to 1. I want to take a ramp that goes just hash and 1 minus hash, right? That will be the ramp up and ramp down, right? And that trivially, the half, it does a trivial thing. But if I take another value, if I take this, okay, I'll get those two values. But what I want to do, what is the tent map? What do we call the tent function? Do we have a tent function? No, we don't. Do you understand what I'm talking about? Tent function goes up to, if I say plot abs of x minus a half, I think. X goes from 0 to 1. Well, apart from the fact it's the wrong way up, I could get, is it a half minus x? How do I get this the other way up? And I want 2 times that, is that right? Ed, do you understand what I'm doing? I just want 1 minus that, right? Are you paying attention, or are we just?
Yes. However, I'm on a very bad connection.
Yeah, strictly speaking, if you want the tent function, it should be 1/2 minus abs of x.
Okay, well, fine. So that would be a nice, thank you. Okay, so what I want, let's put those 2 functions, tent functions in there. So I want this, let's say I want this function, and I want the other. What was the other one? The other one was just 2 times abs of 1 minus x, like that. So that's those 2 tents. Well, they're tents different ways up. Oh, that's jolly. Okay, so let's say, I don't understand. Why am I only getting 2 values at each step? Do you see what I'm seeing? Right, so at each step, I just get 2 values for some reason. So here, that's saying if I were to take nest graph of this, like 1/3, 5 steps. Oh, well, maybe that's obvious. Is that obvious? That's probably obvious. Yeah, the question, what I'm trying to do here is multi-way functions over the reals. That's exactly right. So I'm trying to figure out what is a natural set of functions to study for multi-way systems over the reals. Okay, cubic Bezier seems kind of complicated. I'm going to, let's see whether we can do this with simple. So, we've got these linear functions. So one thing we could do is we need pairs of linear functions, right? So one thing we could potentially do is, because we're trying to understand, is a floor function. So we could say, for example, is this going to work? No, we could say fractional part. Okay, let's try this. Let's say fractional part of 2 hash and fractional part of 3 hash. What will that do? Fractional part of just 2 hash will give us a standard shift map. Oh, interesting. Okay. All right, so this, is this obvious what this is doing? How many points is this giving us? How many distinct points is this giving us? So I'm asking. If I look at this and I merge, well, actually, really what I want to do is I want to do a union of flatten here. And then I want to ask how many distinct points. Okay, so this is, so it could be the case that we have an exponentially increasing number of points, but in this case, we don't. Am I making sense? No. Shall I go back?
That makes sense to me.
Okay, so for what value? So let's say we have a 3 halves here. What's this going to do? Oh, interesting. Look at that. Okay, so for 3 halves, if I say length of that, then I will get something which increases roughly exponentially. So let's take a look at that quantity here. Okay, so this is, I bet this is related to, so is that, there's some density result for powers of 3 halves, right? So, okay, so this is what this is doing. This is filling in and becoming denser here. So if I were to take this and I were to nest this, like, let's say we nest it 50 times or something, and then I were to make a histogram of these, actually 50 may be a big mistake. Let's do 20 times, because there'll already be lots of points. Oh my gosh. I don't want that. I want just nest. Actually, what I want to do is histogram, map histogram over that. Okay, so what this is showing, rather bizarrely, wow. Okay, so what I would have expected here is that these things will become uniform as you increase the number of points, that eventually you would have a uniform distribution on 0, 1.
I believe golden ratio might do that instead of 3 halves.
I don't think so. I know what you're thinking, but I don't think it's right here. I mean, we'll see. We will see. Well, you're righter than I expected. But it's very weird that this isn't uniform, because what you're thinking of, I think, Ed, is if I were to take just the pure unary case, if I were to just say nestless, this golden ratio thing, fractional part of the golden ratio, like that, right, starting from some random number, right, and I were to go 20 steps or something, then I would, if I took that, then I will start to get, that will give me uniform distribution eventually. Let me do 200 steps, for example. I mean, just to understand here, yeah, that will eventually become uniform. Let's do 1,000 steps. Yeah. definitely. Let's do 4,000 steps. Well, heck, I'm pretty sure it becomes uniform, and I don't understand that. Fractional part, is that because of, that looks like it's some kind of value of fractional part of 0.618, right? Why
Yeah, that definitely. I don't understand why though.
Because what is the case, if I were to take this histogram of fractional part table, fractional part of golden ratio, and I'm going to do this carefully because I don't want to mess this up because it will go crazy if I do the wrong thing here. N of golden ratio to the power n, so to speak, numerical value of golden ratio to the power n, table that up to 1,000. I predict this is going to be nice and uniform. What happened here? Fractional part of golden ratio to the n, right? That's like where the plant puts its leaves. Yeah,
That's the multiples, not the powers.
I just gave, oh. Good point. There you go, perfectly uniform. And now if I look at powers of multiples of 3/2, what the heck is that? Oh, fractional part of 3/2 is that there are only two possible values, right? Yeah, this goes 1/2, 1/2, 1/2. Okay, so we don't quite understand this. It's a little weird. I see. The fractional part of powers, of irrational powers, is presumably related to Benford's law. Is that a true statement? It's presumably one of these logarithmic distributions. Okay, so let's go back here. Again, what we're trying to understand is, we're trying to understand how to think about continuous multi-way systems. And the question I'm going to ask is, what is the analog of causal invariance for a continuous multi-way system? It's some statement about measure. And I was trying to actually derive these measures. And again, that might be a Jonathan question. If we are asking...
Right. It's divergence freeness of the natural multi-way measure.
All right, well, let's understand that. So, I mean, what normally, this would be a mapping. Normally, this would be a 1-to-2 mapping, right? Okay, so normally, our system, whatever it is, x goes to, some function f of x, g of x, will be a 1-to-2 mapping, right? But because of convergence, because of these, it isn't always a 1-to-2 mapping. However, that's only true in the limit, right? Because for any, if the numbers are not commensurate, so to speak, you'll never actually collide, right? For any actual finite iteration count, the numbers will never be identical.
Right, which is why, I mean, as I mentioned weeks ago in the quantum computing discussion, that you have to consider the case where the output set is an uncountable set.
I don't think you have to consider that. I think you can consider the limit. I mean, that's what you get. So the
limit of a countable set is still countable.
Let me give you an example, okay? Unfortunately, our friend Bernat couldn't join us for this, but
yeah, the trees example doesn't work for the same reason I explained in the last stream.
Why not?
Because it's still countable.
But it's still the case that, you may say it doesn't work, but it's still the case that the limiting values are identical. Right? So in other words, you have two trees and they are converging. Look,
Yes, so then but then it's no longer equivalence. Your isomorphism function is not a statement of equivalence; it's a statement of convergence. And in fact, it's a somewhat screwy version of it. It's certainly not uniform convergence.
Okay, well, let's think about that for a second. Okay, so your claim is that you can't define causal invariance basically in the same way for a finite multi-way system over the reals. That's your basic statement, right?
Well, obviously you can. As I say, if your isomorphism function is a statement of convergence rather than a statement of isomorphism.
I understand, but that's a limiting. Okay, that's the question: is causal invariance, right? So causal invariance could be. I mean, it is already a statement that the limit as t goes to infinity of this thing resolves the branch pairs. So what is the analog of resolves the branch pairs? It means this mapping better not be an expansive mapping. So it's normally a 1-to-2 mapping, right?
Right, it has to be divergence free in the continuum limit. But to derive
what do you mean by divergence free? You mean it's a 1-to-1 mapping in the end, or what? I don't think
no, it can be 1-to-2 as long as there's a point in the neighborhood that's also 2-to-1, so that globally it's divergence free.
What is that notion of is there a notion of sort of average injectivity? Because that's what you're talking about, right? The thing is yeah. I mean, in the end, what we would like, okay, so the mapping from the t equals 0 state to t equals infinity, we want for causal invariance, we would like that mapping to be injective. Is that a true statement? In other words, if we take a measure at t equals 0 and we look for the measure at t equals infinity, and the system is causal invariant, what should be true about those two measures? I claim those two measures should be the same measure. Right? So it preserves the measure. For causal invariance, it preserves measure. Okay, so what does it mean? So one thing, see, this is a little different than what we were doing here, because saying it preserves measure is a little different from what I was doing here, because here I was taking individual values and I was iterating them, right? But to say that it preserves measure is to say we start off with the distribution at the beginning and we are applying this function to the distribution, right? And going and then we're asking whether.
Right, this is why you need an uncountable set, because you're starting from a countable set of initial conditions. So your initial conditions have measure 0 with respect
I agree
to
with that. Yes, I agree with that.
Range of the functions.
So okay, I got confused by
a measure. Your codomain has to be uncountable. To define a non-vanishing measure, that is.
Okay, so your basic claim is as soon as we go to real multi-way systems, it's no good to have a finite number of initial conditions. Our initial conditions, we're forced, by having continuous values, we're forced to have a whole sort of measures worth of initial conditions, is your claim.
Right, well, otherwise the probability of merging is 0 almost everywhere.
Yes. Well, still, okay, so my question is there anything interesting we can conclude about multi-way systems over the reals, even if we can't get a definition of causal invariance in that case? So one of the questions would be, under what circumstances is it uniform? Do we end up getting uniformity in the system or not? So for example, in this case, for some reason, we seem to be getting some weird function of x that isn't uniformity. See what I'm saying? Which I'm pretty surprised by. I mean, I think that this, let's see what happens if we just blast this with iterations, see what it does. Okay, so let's say we go here, nest, let's go to 100 iterations here, and then let's go ahead and make the histogram of that. Now, I mean, it's worth realizing that we are completely, the machine arithmetic that we're using in this default case is going to be completely wrong for any individual point. I mean, to demonstrate that, oh, come on. Okay, let's just try something slightly more modest. Let's try 30 here. Even that is big. So there must be a lot of values in here. What is this function? So I mean, this is the function we get by iterating fractional parts. So the naive thing to do would be, so it doesn't do us any good to iterate hash. It'll have to be iterating. What happened when we did hash 2, 2, and 3? We got a small set of values, right? Oh, come on, why is this taking so long? How many values are there here? Are there 2 to the 30th values? That's a bad idea. Help. Yeah, it's never going to merge. So okay, if we go to 22, that'll be 2 to the 22 values, which is still somewhat civilized, right? Oh, that's very civilized. We should be able to go to 22 to the 24. Okay, let's go to 2 to the 24 values. Okay, what is that function? Look at that. Isn't that weird? That histogram? There's enough values, we should be able to do that. Okay, that's officially weird. So that's the histogram of values that are obtained by taking the multi-way system for fractional part of 2 and 3 halves. So let's see what happens in the case of, say, 10 here. Let's say we have 2 and 3. Now there we got something quite trivial, didn't we? Even that's not trivial. All right, what on earth is going on here? How much does it depend on the initial condition? Is that basically excavating digits from the initial condition? So let's say we say 0.5 here. Okay, that's going to do something trivial. Okay, let's say 1/3 here. I see. So for 1/3, we just hit the 1 from that. But if we take something non-commensurate with 3, oh no, I see. It's the LCM then of 5 and 3, I think. It's going to give us the denominator.
But 7 might be different.
Why? It's going to give 21. What is it doing? So you say that it's some multiplicative order function or something of
to continue the decimal digits in the fraction. 1/7 has 6 in the repeating fraction.
Why does it have anything to do with decimal? It's fractional part. It's not decimal. It might be ternary. Okay, so that is the values from 1/11. Why is it producing those values? So by the way, if we do this now from nest graph, we could do this in nest graph, and we should actually get a non-trivial graph where, notwithstanding Jonathanism, so to speak, we'll actually get merging, right? For 1/11, we should get, that thing should show mergers.
Yeah, because we're not using anything, we're just using rational numbers.
Right. So let's take a look at this one. Oh wow. It's a cycle. Let's take a look here. Okay. Okay, is that obvious? Let's label the values. Oh yeah, it's a circle of, it's like chords or something, isn't it?
You're just multiplying a number by 3 or 2, and then until you get 0 mod 11.
Yes.
You're just seeing the structure of modular arithmetic.
Okay.
Which, by the way, brings me on to a question I had about what you were doing earlier. You were asking about the, why you get merging in 3n+1 and 2n+2, but not for 2n and 2n+1.
Yep.
Isn't that just a modular arithmetic story as well?
I don't know. Let's figure it out.
Right? Do you have those examples back up in the notebook?
Yeah, I do. What's this? Why isn't this just a pure cycle like this again?
I think it is, just not done cyclically.
No, I mean, this is just arithmetic mod 13, right? If you plotted the integers mod 13 with with times 2 and times 3 as your generators. It's the same group structure.
I see. So you claim this is like a Cayley graph of a group where the generators are multiplication by 2 and 3.
Yeah, it's the subgroup of Z13 with those generators, isn't it?
Yes, I think so.
Yes.
So Z13. Okay. So let's predict something interesting along those lines. What's a group that has some interesting structure there? And then we'll come back to the modular arithmetic for the AB thing.
Obviously, prime groups of prime order are more interesting than groups of non-prime order.
Yeah, I understand that. So let's say 17 or something here. I see. So that becomes trivial. But certain cases, it probably has to do with the subgroup structure in yeah, all right. So then this fractional part business. I mean, okay. Let's go back to the previous thing. So Jonathan had an idea about modular arithmetic over here.
Well, I mean, my idea is pretty trivial, so it may just be stupid. But
well, if you take the modular arithmetic version of this, if you take this mod something, yeah, go ahead.
No. I'm saying it already is modular. I mean, the explanation for why there's merging in the 3n plus 1, 2n plus 2 case is modular arithmetic, right? It's because you're basically asking, are there numbers which are congruent to 0 mod 2, which are also congruent to 1 mod 3? And the answer is obviously yes. There are things like 4, for which that's true, right?
Okay, so your claim is,
whereas in the 2n and 2n plus 1 case, you're asking, are there numbers that are congruent to 0 and 1 modulo 2? And the answer is obviously no, so you don't get merging.
Okay, so the coincidences you claim
are instances where there is a number n that is both congruent to 0 mod 2 and congruent to 1 mod 3.
Well, okay, so wait a second. So in order to, the coincidences are cases where two numbers, so you're saying, look at the coincidence, look at all numbers mod k, and then the point is that this graph, whatever is true about this is also true mod k, right? So in other words, we're saying this nesting, if we did that,
I'm saying something much more elementary, right? It's so in order for there to be merging, if you have two branches, of one produced by a 3n plus 1 and one produced by a 2n plus 2,
yep,
right? In order for those branches to eventually merge, there must be some number such that because
yes, I understand, but branches are not pure play 3n plus 1 repeated and 2n plus 2 repeated.
No. But once you've had one 3n plus 1, that structure will persist. The fact that produces something that's 1 mod 3, and that 2n plus 2 produces something that's 0 mod 2.
I recommend that we look at one thing.
That remains true independent of how many previous things you've applied.
Oh, I agree.
Right.
That these things map. The whole point is, so if we were to take modular arithmetic here, mod 3, for example, okay, then that graph, the whole point is that if we do that, what we're saying is that there's presumably it's a subgraph of this or something, or some factor of this graph that has this property.
Sure.
Is that right? So mod 3 and mod 2, you're saying that we could mod out numbers. We could take only numbers of a certain form. No, this is saying, if I label that graph, right? Okay, that's saying numbers mod with respect to this iteration, numbers mod 0, numbers that are 0 mod 3, always map to numbers that are 2 mod 3, and so on. Right, so that tells us, let's compare that with the case where, I'm a little bit confused how this compares with the case that we know, like the 2n plus, what was the case?
Yeah, I mean, I'm not talking about mod k, right? I'm talking about the thing I was mentioning. So obviously the reason why 2n and 2n plus 1 don't merge is because there aren't numbers that are both congruent to 0 mod 2 and congruent to 1 mod 2. You can't have a number be both even and odd at the same time. But you can obviously have numbers that are congruent to 1 mod 3 and congruent to 0 mod 2. because 4 is an example.
I'm sorry, I still didn't get this. So you're saying we take a number.
Look, all number, for any n, 3n plus 1 is congruent to 1 mod 3. That's what 3n plus 1 means, right?
Yes.
And for any n, 2n plus 2 is congruent to 0 mod 2.
Yep.
The question of whether those branches merge is the question of whether there exist numbers that are congruent, that are both congruent to 1 mod.
I see what you're saying. I see what you're saying. So you say, look at the last. Okay, so
4
you're
is
saying,
congruent to both 1 mod 3 and
right. A merger requires that the last step not go astray by having numbers that aren't, by having numbers that don't match mod k. Right, so forget about where it went before, but the very last step where you compute, right, where you compute 3n plus 1 and you compute 2n plus 2, it better be the case that for any that.
Yeah, it's a necessary condition for merging, that obviously the two sides be congruent modulo their coefficients.
Right.
And so at least for the two cases that we were considering, the 3n plus 1, 2n plus 2, and the 2n and 2n plus 1 case, that explains why those both do and don't merge, respectively.
Okay, hold on. You're saying, let's see, this case here, the 3n plus 1, 2n plus 2 case, you're saying that there exists an n such that mod 3, so there exists an n. Okay, so what this requires that n is equal to 1 mod 3 and n is equal to 0 mod 2. We have a nice function that determines, what is that function? Is that the Chinese remainder function that determines what value of n will satisfy those conditions, right?
You can do that, yeah. But 4 works.
I understand that. Because the smallest number which satisfies the integer congruences so that its remainder mod m. So this will be the Chinese remainder of equals 1, 0. I just believe in using computers when you can. 3, 2. There it is, 4. Okay. So now your statement is that, so what was your prediction for another one?
So you were asking why would this argument fail in the case of 2n and 2n plus 1? And that's kind of obvious. Again, it's like, you can't, a number can't be congruent to both 0 and 1 mod 2.
Yeah, so for example, e.g. for 2n and 2n plus 1, right, the case of the binary tree, right, the Chinese remainder theorem is going to fail. Right, so this would be the case where it equals, well, I mean, it's kind of stupid, but I could just type it in. I could ask for this case and it'll just say, forget it, doesn't work. Okay, but so you're saying this is a necessary condition for merging, but it's not saying whether it will be sufficient for merging.
Right. No, I mean, I noticed it was sufficient to explain all of the examples you were asking about.
But this one, for example, isn't causal invariant. The 3n plus 1, 2n plus 2 isn't causal invariant.
But it does
has
have
merges, but not enough.
Right.
So the density of merging is a different issue.
Right, which probably has to do with the value of the Chinese remainder.
Or the total modulus, or
well,
whether there's a divisor.
But let's see whether we can work this out, because I mean, what you're saying is,
in general, you would expect the smaller the Chinese remainder theorem gives you, the smaller the value, the more likely it is to be causal invariant.
Okay, let's say Chinese remainder estimation. We'll see whether this is true. Okay, so this is going to give us for A, B, C, D, right? We're going to make a table of the Chinese remainder, and this is the first one is the is the BD, right? And the second one is the AC, if I'm not mistaken. But let's see, we need to take A and C mod, right? Mod B. We need to say A mod No, I'm sorry. We need to take this first, right? It's B mod A. Is that correct? That's the case we want. D mod C, because we want the modulus, want the remainder. Because if in this case here, right, we're considering 3m plus 1 is that's A is 3, right? 3 there. B is 2, but then we want to take this thing mod that. Do you believe this? Yes, no, maybe?
Looks about right.
Okay. A, B, C, D. C4, D4. Okay, let's... Okay, so there are a bunch which... Okay, so there are a bunch here. So let's replace the pure Chinese remainder by infinity, right? Is that the correct thing to do? That's like,
yep.
Those are cases where there cannot be a merge.
Right.
Right? And you're saying, so, okay, so let's take this and I'm going to just hack it here. Underscore Chinese remainder, arrow infinity. Okay, so now we want to compare that. So those are the values of the Chinese remainder quantities. And we want to compare those to the data here, right?
Right, so my prediction is the ones which give big values of the Chinese remainder theorem are not going to be causal, for the Chinese remainder, are not going to be causal invariant.
I got to have falses here.
Yeah.
Okay, so let's...
1 or 2.
What's that?
The ones that are 1 or 2 are quite likely, I would argue.
So let's, I think what we want to do then, how do we want to do this? Do we want to transpose those two arrays? How do we want to do this? Got a good idea how to do this? How to do these comparisons? Well, let's just transpose the arrays together to begin with. Okay, who knows that transposing well enough to be able to do this? Okay, we've got a rank 4 array. And what do we want to do? Ed, anybody else? What do you know? Do you know how to do this?
I keep doing it until I get it right.
Ed, that's so unconvincing. Okay, all right. You know, I'm going to do the same thing, though.
That's already quite useful, though. Oh, okay, there you
go. Right. Okay. So now, what is the Jonathan claim? So let's take these and let's just flatten them all out. Flatten to level 3, I reckon. Okay. All right. So now, what do we want to do here? We want to sort by. Let's go ahead and sort by the falses and sort by the trues. Okay. I'm sorry, Jonathan. Your claim is not looking very convincing. I do not see a big difference here between the truths and the falses in terms of whether they are, unless we did something wrong here.
No, that looks okay. I mean,
well, let's just make the histograms here. So we could take cases of that, comma blank, comma true. Well, let's just do X there, and let's say arrow X, and then let's histogram. Let's just do counts of that. Okay, so that's the number of times in true that we get these different values, and this is the number of times in false we get these different values. Oh. Well, so first point is, okay, there are no trues, which is obvious, for which the Chinese remainder is unresolvable. Right?
Yeah.
That was line 553. So let's
take... It does look like it's skewed a bit more towards the right.
I agree. 553. Right, I mean, so let's histogram them. So this is the trues. This is the were causal invariant. And that's their Chinese remainder quantity. And then let's look at the falses and let's see what their Chinese remainder quantities look like. Well, maybe. Okay, so this is the claim here. There's still a bunch of small Chinese remainders which were false according to this. Now, of course, we don't absolutely know that we've got the right answers for these trues and falses. Okay, but so we've got some criteria from the Chinese remainder theorem here. That's good. Now I wonder whether there's some other quantity, other number theoretic indicator beyond the modular arithmetic. Then yes. Okay, let's see. All right, so let's go back here. We were looking at the rational number case here. Yeah, I don't think the digit, Richard was commenting on digit sequences. I don't think digit sequences are related to this. I think this is purely a question of a group theory, a subgroup question for whether these things generators, whether these generators 2 and 3, I don't think the fractional parts, are they giving digit sequences? Let's see. The naive thing here, let's just understand this. So if I say nest list of fractional part of 2 hash, comma, give us your favorite number in well, let's do a favorite number in binary. So let's say base form 1/7 base 2. Oh, come on. Boring, boring, boring. Let's say n of that, comma, 20 and base 2. Okay, so there's a recurring binary, whatever. What is a binary number? What is the analog of a decimal for binary? I don't know. But anyway, so if we do that, and we look at this here, and we look at, okay, so we're going to do this, and we'll then say 20 steps or something here, then what we should find is that the leading digit here, so if it's greater than a half or less than a half, will be just a map of this, this thing here. So if we say, let's see, we want to say, I want to say the integer part of 2 times that. Oops, integer part of 2 times this. Yeah, so I claim that will be a precise map of that 1/7 until we run out of bits, and then it will go crazy. Right? If we do this to 40 steps, this is what we're seeing. We're seeing then eventually this thing will break down because it will no longer, yeah, there we go. It just broke down there, right? So what we're seeing there is the failure of I mean, if we did this with machine arithmetic, it will break down a lot sooner than that. But this is arbitrary precision arithmetic breaking down only at a certain level. Okay, so with machine arithmetic, the thing goes bonkers somewhat earlier than it goes bonkers at 20-digit precision. But so that's the relationship with digit sequences to fractional part. If we were to do this to 200-digit precision, then we will be hunky-dory even for 100 iterations here. I don't think that's related unless I'm missing something. Is that related? So in one of these things here, we are essentially mining. Yeah, we would be mining the digit sequences of that initial condition, except for the fact that if the initial condition is rational, we're not worrying about that. Let's see.
Also, machine epsilon gives an interesting convergence criterion in the continuum case.
Yes, I understand. So machine epsilon being your criterion for your.
If you want to do this with genuinely countable sets,
right? Then one possibility is we could do causal invariance up to epsilon, so to speak. So that one possibility is. So either one possibility is, okay, so the cases are, case 1, consider only non-zero measure, standard measure, initial conditions, i.e. not countable initial conditions. Or case 2, consider merging up to epsilon. Okay, let's think about merging up to epsilon, for example. How do we think about that? What would that be? So in our essentially what we're doing is we're fuzzing out the tree and saying there's sort of a catchment area for every branch when the, if it ever gets nearer than epsilon to another branch, it's captured. Sort of interesting as a sort of a, insofar as we've thought about using multiway systems as models of machine learning systems, that will be an interesting way to do that.
Right. I mean, it's also, I mean, in a way, it's another way of thinking about a completion. You're basically saying when events are space-like separated, only, you know, but only within a very small distance, then we merge them.
Right. This is analog, is a continuum analog of a completion. All right. So then what we could do here, okay, so let's write both of these cases. Okay. So the non-zero measure case, what we're doing is we're saying, so for this one, where were we here? We were saying, okay, so first of all, okay, for the rationals, we've got a whole different story, right? For the rationals, for these arithmetic functions, it's a nice closed system and rationals map to rationals. And typically rationals in a case like this are mapping to rationals with the same denominators. Okay, as soon as we have nonlinear functions there, we're going to have crazy stuff with rationals. But here, so the first case here is we've got an initial measure. So let's imagine that we're mapping, let's imagine here, go back to this again. Instead of mapping, what we want here is instead of mapping that, okay, so mappings of measures, basically. So this is kind of like an ensemble here. What we want is an ensemble in which, for example, we take range 0, 1 in steps of 0.02, and then we map that, and then we ask for a histogram of those things. So that's asking, that's what happens to that measure, right? At the beginning, that will be a uniform measure, right? And this is asking, what does that measure do as we iterate it? Make sense? Yes? Oh gosh, this is huge because that iteration is okay, so what we're finding is in this measure, the thing that started off with uniform measure is winding up with some kind of weird measure here. Oh, wow. Cool. What is that? So there are values. Oh, but I wonder whether that's just a reflection of the 0.02s at the beginning. Let's see what happens if we try 0.01. That may be because those numbers are too, yeah, I think those numbers are too round. What we want to do there is we want to say random real, let's say 1, how it works, 0, 1, comma 100, for example. There's still structure there. Maybe that structure is not real. Maybe that structure is just because we're not averaging over large enough bins here. Let's try 0.04. Probably that's going to become uniform. Let's try, if we do, let's try blasting it with more values here. Let's blast it with 1,000 values there. Come on. Okay, I believe it's going to become uniform. Okay, so what this is saying is the measure, that initial measure maps to something, uniform initial measure maps to a uniform measure under that essentially multi-way, continuum multi-way system. That makes sense? So in fact, an interesting question. So insofar as that measure maps to a uniform measure, what does that tell us about causal invariance? Does that tell us, does the fact that the measure that we get out is the same as the measure we put in, is that a statement of causal invariance or something different?
When uniformity is not a statement that the measure is the same, it's a statement that the distribution of measure is the same.
Fine, but the measure itself is computed. I mean, our measure here is, I don't understand why those aren't the same statement. Because we've got we started off. So I mean, the question here is, what we're doing is this multi-way system is branching. It's generating all these points, but in the end, the distribution of those points is the same as the distribution of points we started off from. Although I guess I don't know what statement that's really making.
But I can take two sets that have the same distribution of measure, but their measures can be different.
Yeah, I understand. No, and it doesn't really say anything because it doesn't say for any particular. This is giving the ensemble average for an ensemble where you have a bunch of different initial conditions. This is the ensemble average.
Now, if this were a multi-way causal network, then we could infer something about causal invariance because it would be informing us of uniformity in the multi-way causal graph.
Yeah, but this isn't a causal graph, and I have no idea how to get the causal graphs for these.
No, I know. Yeah, so because it's a states graph, you can infer things about the uniformity of the possible states, but you can't infer anything about causal invariance, I think.
Right. But so my question is there any? Okay, so in this mapping from uniform, I mean, this is very similar to standard dynamical systems theory. What we're doing here, in fact, it barely cares that we just got two functions in the act, and honestly, it just doesn't really matter very much. I mean, it's just going to be very, very similar to all the results of standard dynamical systems theory, I think. So, for example, if we take this, okay, let's take the following thing. So let's take, let's just do standard logistic map, okay? So let's say we go 2 hash, 1 minus hash, and let's just say for fun we do 2 hash and 3 hash, 1 minus hash. Okay, so I claim that that's going to just give us the same results. Or let's just say 2.2 times that. And let's not do as many steps. We don't really need as many steps, I don't think. Oh gosh. Well, I'm wrong. No, I'm not wrong. That goes to a fixed point. That goes to a fixed point. That's correct. That's exactly what I would expect. So what this is now doing, now as we tease these apart, okay, so what this is doing, which is a little weird, is at 4, we will have paths that are purely chaotic paths. And this may not be long enough to see the chaotic paths, but this is a bizarre mixture of the chaotic logistic map and a non-chaotic logistic map. Does that make sense to people? So at 4x1 minus x, the logistic map, I mean, if we just make a nest list of 4 hash 1 minus hash, right, then what this is going to do very rapidly, well, if we do the 2 case, it's going to go to a fixed point. And we pick a random number, random real between 0 and 1, and then we just go, I don't know, 50 values, and then we make a list line plot. This is going to go to a fixed value of 1/2, right? If we do the same thing with 4, then this is in standard kind of chaotic, this is going to produce something like that has essentially a uniform distribution. I think this has a uniform distribution on, so eventually let's just see what this does. If I say histogram of those values, let's go a little bit further, let's go 500 steps here. Histogram of those values. Oh yeah, that's right. It has some distribution that isn't completely uniform. It's square root of 1 minus x squared or something. So this is like, let's do 0.05 here. Yeah, it's going to be, let's go 5,000 of these. Yeah, that's going to be the square root of 1 minus x squared, I think. Okay, so that's the distribution of values that we get from this. But now what we're doing here is something I've never seen done, which is we're doing the combination of those two functions, right? We're doing, and so what we could do in principle, we could just say, in fact, we could add a parameter here in which we say, so those two functions together are producing, let's go a few more steps here. Let's go 40 steps or something. Oh, no, we can't do that. We can't do that. Help. We can't do that because this is, I mean, we could in principle do that if we sampled. So this is like a binomial tree thing that people use for finance, right? You're sampling many possible cases here. Let me remind myself how the binomial tree business works. Let's see, binomial tree option pricing. Yeah, 1 yeah, I think what you're doing here is, let's see whether this is a, look at this. Whatever. I'd be better off writing it in our language, but whatever. Okay, so this is the same, I think it's the same type of thing. You're doing, right. Yeah. Yeah, so essentially, that's interesting. So in other words, this is sort of an idealized case of something like this binomial tree thing, I think. But I think what one's going to find is again, there's this sort of combination of two functions here. And that's what we're seeing here is two copies of that square root of 1 minus x squared thing. Okay, so that's the case where, so that's mapping, basically it's going to be a story of standard dynamical systems theory, mapping an ensemble of initial states onto final states. Because your claim is you can't map individual initial states onto final states. Okay, so the next question is the machine epsilon case. Let's see. Okay, so machine epsilon, yeah, is that somebody is mentioning on the live stream is the difference floating point number to the next representable number in binary. But we're not necessarily using, you know, the actual machine epsilon, which is this for my particular machine. And if I say 1 plus this, and then I subtract 1 from it, I'll get machine epsilon again. What happens if I see. If I say 1 plus machine epsilon over 2, I have a bad feeling, and then I subtract 1 from that, then, oh, arithmetic is not commutative anymore. So sad. Arithmetic doesn't have inverses anymore. So sad. That's what you get with machine arithmetic. If you do let's see, if you do you know, if you use arbitrary precision arithmetic of the kind we have, then you don't get this result anymore. But okay, so for our purposes here, we're not going to hack it by using actual machine. Well, we could actually hack it by using actual machine epsilon as our bucket size. But so the question here is now, if we were to combine things when they are machine epsilon apart, how will that work? So in other words, we're taking something like this, and what we're saying is we're doing, okay, so this is the bucketing case, epsilon bucketing, so to speak. And what we'd be doing here is we'd be saying at every step, we'd be saying union, if I'm not mistaken, with the same test, that is it less than epsilon apart? Is that right? Same test, arrow, abs of #1 minus #2 is less than, let's say, 0.01. So do you think that's right? Comments? Jonathan, do you think that's right?
Sorry, I was doing something else.
So I'm trying to actualize the same test.
Okay, that same test looks okay.
As a matter of fact, we could even do a nest graph with this, right? Because we can actually do a this nest graph should actually work. So if I start off with let's say 1/7 here. So what that did was, in this particular case, that's mapping, right? That just maps. After a while, it will have visited it's a complete graph, right?
Well, the undirected, no, it's not. No, even undirected, it's not. But obviously in the 1/7 case, because that's just the arithmetic mod 7, it doesn't matter whether that's your same test or whether equivalent to your same test.
Okay, so let's try pi here. Oh gosh, look at that. It's got some merges. It's got some merging. That's cool. Let's try pi for like 10 steps. Oh, that's cool. So this is going to be a continued fraction play of some kind.
But now what happens when you increase the epsilon?
Well, it's going to merge more.
Yeah.
This
But
is
I want to see
that's
how.
what's interesting. I mean, so if we go right, so this is causal that. Oh, why didn't that merge more? Okay, let's try abs less than 0.1. Okay, I am confused.
Well, it changed.
Did it?
Yeah, that's a different graph.
Well, okay, but let's try a smaller graph. Let's try just 3 steps. Okay, there's that. It has one merge in the 0.1. Let's say it's less than 0.4. Okay, huge. Okay, what did that do? Oh, that just doesn't have very many buckets. Right, because this thing.
Also,
right,
you're only applying the same test, on each step, so to speak, whereas you should be applying it across everything.
Yes, you're right. Okay, you're right. So how will we do that? So what we want to do then?
You can do that in Multiway System by just doing a state equivalence function.
Okay, let's do it. Okay, so what we want is that the that's ornate for a state equivalence function, if I might say so. Okay, so what we want here, let's look this up. Where was it?
More ornate than hypergraph isomorphism?
No, I admit it's less ornate, significantly less ornate than hypergraph isomorphism. All right, where's a version of this that is not totally grotesque? Okay, let's write the version here that we need. Okay, so we'll take out all the stuff that is, okay, so all this stuff, I'm just going to put this to identity or something here just so that we have something in there and we don't get confused because these are wrong. Make sense? Event application function, can I leave that one? What do I put for system type here?
Any string, doesn't matter.
Okay. Event selection function identity. And what's this? That's garbage right now. That's just me hacking something here. Yeah, that's me just hacking some crazy situation there. Okay, all right. So now state evolution function is the state evolution function is just fun, the function, right?
Right.
Correct?
Right.
Okay, the state equivalence function, however, is, well, let's put our equivalence function, let's call it a MFS epsilon. Okay, so the state equivalence function, we'll put that here, and we'll put the value of epsilon here. Okay, and the state equivalence function should be abs of #1. Is it a thing with #1, #2?
Yep.
Is less than epsilon. Like that. Agreed? Okay, so now we say MFS epsilon is our friendly fractional part. Initial condition is pi. I probably should make this numerical value of pi. I'll just make it numerical value of pi for now. Otherwise, it's going to do a symbolic reduction of the fractional parts, which is a little bit messy. Okay, let's say 5 steps, and let's take a bucket size of 0.1, and what we want to do is states graph structure, right? Is that correct?
Right.
Oh, okay. So that is a very causal invariant thing. So as we go down here to 0.01, No, something's gone wrong here. There's no way these things are equivalent anymore.
Wait, that's just commutativity.
Oh, I see. So you're saying basically, once we have this epsilon structure, we can put any functions we want in here, and it's going to be interesting, right? So at this point, then we can go back and we can go ahead and, so this is a good idea, actually, this epsilon bucketed thing.
Right. So okay. Obviously, you weren't seeing commutativity in the nest graph case because multiplication is not commutative over reals in machine arithmetic.
That's an interesting statement. I mean, yes, I agree. Let's just put in some random thing here, just for the sake of just seeing something, and then we'll try and take a look at what. Okay, so there's a graph that we have that is rather non-causal invariant. Okay, so let's increase the bucket size. Okay, so far nothing happened. So let's increase the bucket size again. Okay, I'm getting suspicious now. No, I'm very suspicious now. What's happening here? Because at this bucket size, we should expect, we go more steps here. We should expect, I don't even understand why there are so many, that bucket size, why are there even so many independent points there? I don't understand what the union did. So your same test.
Yeah, I mean, there are big numbers there.
Oh, silly me. Silly me. I need to do 1 over pi here. It needs to be between 0 and 1.
Right.
It's going to mess up. Well, that now is a pure... I'm now confused. I'm very confused here. Why is this not? So this should be between 0 and 1. Okay, every number is between 0 and 1. Now, why are these numbers, when they're pairwise compared, right? You should be pairwise comparing every pair of numbers. If I'm not mistaken.
Right.
Why? So should we look at what it's actually comparing inside the code? So should we just echo this thing here? How do we want to do this? I mean, we could also just put that criterion in an echo in that criterion. Let's just understand, what does it think the state equivalence, what is it assuming about transitivity or something of the state equivalence function?
I don't know. I'm also wondering if it's something else. I mean, instead of getting the states graph structure, can we look at the all states list? This may be because of not knowing which of the two things to keep.
Yeah, I think it's because effectively it's assuming transitivity and it just isn't true.
Right, but if my conjecture is right, I think we should see a difference in the states list.
As what happens? So you say with 0.001 and 0.01, let's say. Not seeing it.
Go a bit higher. There we go.
Okay, so what's happening here? So it's managing to prune some of them.
Right, right.
But the correct pruning, I mean, it's kind of interesting. It's very similar to the stuff we were just talking about earlier today about blockchains and what branch survives, so to speak, is when you have, when you're trying to do a double spend, so to speak, which, which do you keep?